This is our first video on DSA and problem solving series. Today we are going to see prime number, which is a very basic program. In this first let's see the brute force method, and then I will improve it with some observations. Observing a pattern is like very important in improving the solutions time and space complexity. In this problem, you will understand how much we can improve it with the help of observing the simple thing. Let me first give the basic overview of what is prime number. A prime number is nothing but a number that is divisible by 1 and itself, in which the remainder should be 0. So in this example, when we divide 10 by 2, we get 5 and the remainder will be 0. Here we also call this 2 as a factor of 10. For every prime number, the factors are 1 and the number itself. In this case 11, the factors of 11 are like 1 and 11 alone. So by this we can conclude that for each and every prime number, the number of factors are 2. Open the playground and create a variable. We are going to find that this number is a prime number or not. I iterate it from 1 to 24, that is number. Inside it we are just going to find whether I is a factor of number. For that we are going to check that num modulo I is equal to 0. That means that I is a factor of number. We already seen that, right? So if we found that I is a factor of number, we have a count and we can just increment that count. That's our count. So this keeps tracks of the number of factors. Okay, I'm initializing it with 0. So after if you find that particular I is a factor of number, just increment the count. Where okay, and once the iteration is completed, just check the value of count is greater than 2 or not. If it is greater than 2, just print it is not a prime number. Otherwise print it is a prime number. Got it right? Just check. So 24 is not a prime number. Check for some other numbers like 29. 29 is a prime number. That's it. We are going to observe few more things here, right? I have just listed out the factors and the respective multiplications like that. For once you found that one is a factor, you can say that there is another factor like 22. If you found 2 as a factor, obviously you will say that there should be another factor, right? Because multiplication of two numbers only makes a new number, right? Only with a single number we cannot multiply. So in that case, if we have one factor, obviously there should be another factor. Okay, so the factors are like in pairs. Okay, and also it is repeating. See here, we have 1 cross 24, and obviously we have 24 cross 1. As I said, it is just repeating, and the factors are in pairs. These are the two major things we have to know that these numbers are repeating and the factors are in pairs. So when you see here, up to 4, right, there are no repetitions, and after 6 the numbers are repeating, from the previous part. None of these are unique, right? So why can't we just stop iterating until 4 alone? Just there's no need to iterate after 4, because we know that 6 is a factor, right? Because we already found that 4 is a factor. From that we come to know that 6 is also a factor, because the factors are in pairs. So we can just stop iterating up to 4 itself. Okay, but the thing is, where to stop this iteration? Just look at this. Up to this part, the first number is always smaller than the second number. Did you notice that? And after that, the first number is always greater than the second number. So this is some pattern, so we have to observe the patterns carefully. So we can stop when the first number becomes larger than the second number. That is where we have to stop the iteration. Okay, going to implement that whatever we have seen so far. Okay, the first thing is, we have to stop iterating if the first number becomes larger than the second number. So for that case, no, a for loop is not suitable. So I think while will be much better for this case. For that, I'm creating a while loop. In a while loop, we have to compare two numbers, that is the first number and the second number. We'll be having that in a variable, obviously. First number, obviously we are going to start from 2, right? So, and the second number, so what should be the second number, do you think? So let's have some non-prime numbers, and it will be easy. Okay, for 24, what do you think is a second number? The first number is 2, then obviously the second number is 12. But as a generic, how can we calculate the second number? It is nothing but a given number divided by the first number. Here the given number is 24 and the first number is 2. Obviously that gives us 12. So we have to iterate until first number is less than second number, and then we have to check that this particular first number is a factor of the given number. For that, just check whether the remainder is 0. Given number modulus first number, which is equal to 0. That means there is a factor. Okay, and that also means that there is another factor. Okay, so that is, we can increment the count by 2. And also, if we find a factor, what that means, it is not a prime number, right? So we can just end the loop. We can just print that it is not a prime number, and we are just ending this. Okay, just to break. If not, we have to recalculate the second number. first number also. First number should be incremented by 1, and the second number is nothing but we have to recalculate it again. That's it. And this part remains the same, as there is no change in that. Now just check it now. 24 is not a prime number, and let's try some 13. 13 is a prime number. That's it. Part looks not tricky, but this small change will improve the time complexity much better. So just try to watch the video 1 or 2 times more and try to understand the solution, and try to understand the observation that we have seen before. Okay, and one thing is pending. There is a edge case in this problem. We have seen that the factors are in pair, right? Is it possible that two numbers can be the same? Yes, it is possible. Consider for the number 25, 5 is a factor. Then what should be the another factor? 5, because it is a perfect square, right? In that case both the numbers are same. In that case, is it like makes sense when we increment the count by 2? No, right? So in that case we have to increment the count just by 1, and also here, so we are always checking that the first number is less than second number. But when comes to 25, we'll get a factor only at the point when first number and second number are equal. So in that case it never comes into this loop, because we stopped when it is equal to or greater than the second number, right? So we have to just change it to less than or equal to. Okay, and also here, if the first number is equal to second number, we can increment the count by 1, because both the numbers are same. Or else we can just increment the count by 2. This particular part doesn't make sense in this particular prime number problem, but if you are asked to find the number of factors, this part is mandatory. For now this is not required. We can simply increment the count. So whatever it is, we are just breaking it, whether the count is 1 or whether the count is 2. If it is greater than 0, we are just printing that it is not a prime number. If you are asked to find number of factors, then this is must. Okay, so yeah, let's check it finally. For 13 is a prime number. Let's check for 25. 25 is not a prime number, correct? Am I right? Yeah, that's it. That's all we have for today, guys. So now you got to understand how a simple observation makes a much more improvement in the code. Okay, this looks tricky, as I said before, but this improves the time complexity much better. Similarly, we'll see more problems and more algorithms and more data structures. So please do subscribe so that you won't miss any videos, and support and share it with your friends, and we'll see in the next video. Thank you. Bye.